I'm Priya Crosby, and this week I'm at the British Science Festival in Newcastle, where I was lucky enough to catch up with Chris Frost, one of the scientists featured here, to discuss his work on cosmic rays and electronic interference. Cosmic rays are extremely high energy particles, most of which come from outside our solar system. I asked Chris how these extraterrestrial particles could affect us here on Earth.
Cosmic rays, most people think of them as something out in space, and indeed they are, but when they interact with the atmosphere, what they do is to generate at ground level particles. The ones that I'm interested in are neutron particles. So if you were to put a 10-pence piece on the desk in front of you, that's being hit by one of these neutrons, they're high energy neutrons, at about once a minute. If you then go up in the atmosphere to where aircraft sit, that's about 300 a minute going through a 10-pence piece on an aircraft. And these neutrons are the ones that are interfering with electronic systems. They're effectively reprogramming them. So the interaction of the neutron with the silicon in the device of the electronic system disrupts it. And this disruption of the electronic device can actually make it not work. It can create faults in it.
Have you got any examples where a neutron affecting a piece of electrical equipment has really had an effect on how that piece of equipment might work?
I've got several examples of this, ranging from actually that you might regard as amusing, which is a voting machine in Belgium in 2003 that added 4,096 more votes to one of the candidates because a cosmic ray interfered with the memory state of that system. So it flipped one of the bits from 0 to 1, the 12th bit, that's 4,096, and it added those people to the vote. It was a local election, and so there weren't actually 4,096 people voting. That's a kind of benign example. And then it gets a little bit more serious. There's a 2008 incident of an aircraft where its system was suspected to be interrupted by a cosmic ray, and that led to actually the aircraft doing some dives. It did 2 dives because the control system of the aircraft was not working properly. So it goes actually from the sort of benign and what you might regard as amusing up to actually the really quite serious. And of course what we're interested in is enabling industry to deal with the critical systems and the serious things, but then also the commercial ones. So we're interested in helping commercial industry make sure their products are reliable, like big end server systems and things like this.
And you said earlier that we suspect that it was affected by a cosmic ray. Is there any way we can be sure that it is cosmic rays that's causing this electrical equipment to malfunction, or are we just not sure and it's just a theory? How can we know that this is what's happening?
I think we're pretty sure for many things. The reason why you suspect it is because, in fact, in the report, what it said was they didn't really have enough information to definitely pin it down. In many other cases, what you can do is to do testing on the ground, and that's what we're about. We're about enabling companies to look at the faults, look at the vulnerability of their systems on the ground. And there are many, many scientific papers dealing with the nature of neutrons interacting with silicon devices. So we're pretty sure it happens. We're very sure it happens. But in each individual circumstance, it can be difficult to really pin it down. But it becomes a balance of risk and a balance of probabilities.
Do you have an approximate idea of how common this is? So when something malfunctions, how certain is it that it's due to a neutron interaction with the equipment?
Again, it's a sort of balance of probabilities. If you take something like a 1 gigabit of memory and you put that into an aircraft, some memories will fail every 8 hours. Now, that doesn't sound a lot until you start saying, well, I've got 10 gigabytes, that's now failing every hour. I've got 100 gigabytes, that starts to fail every minute. And this is part of the problem, is that as we're increasing the amount of use of electronics, even small vulnerabilities start to add up to actually almost sometimes near certainty that you're going to see a fault or an interruption in that device. And our job is to enable the electronics industry to look at those faults, look at those vulnerabilities, and devise mechanisms to get over them. So it's understanding the problem that's the key to this. It's understanding where the vulnerabilities are and then enabling the electronics industry to actually overcome that by designing in fault tolerance to the systems.
So I'm fairly convinced this is a real problem, particularly in a world with an increasing number of electronic devices. So what exactly are you and your group doing to try and overcome this problem? What can we do about it?
What we can do about it is to do proper studies. So what we're doing at the Rutherford Appleton Laboratory on the ICIS source, which is the UK's neutron source, is to build an instrument, so we've called it Chip Irradiation, Chip IR, and what we can then do is to pull out of the neutron source a spectrum that mimics the atmospheric spectrum very closely, but it's 100 to 1,000 million times more intense. That means that people can bring their devices or their systems, we can go up to meter-sized systems, put them into our beamline, run them as if they were out in the environment, but of course what we're doing is the equivalent of hundreds of years out in the environment to 1 hour in our beamline. That means that you can fully test these systems, both at the device level, so you can take the individual chip and look at it, right up to huge system level, so for instance server system level, and look at those. And then you can see whether not only your chip has faults, but whether your mitigation strategies are working as well. In other words, that having built in all the fault tolerance, does that actually work? And we can test it to about 100 years in a single hour.
And is this being taken up by lots of electronics companies, or is it a problem that they've not yet recognised?
I think the aircraft industry is well aware of it. The 2008 incident is one example where it increases their awareness of it. But we have already started. We've used a test beamline to do feasibility studies, and we've had major companies coming along and using that, testing the devices, even though we're not optimal. What I'm building is hopefully one of the world's best testing facilities. But in the meantime, we're using the source anyway to do some testing. It's not optimised, but still people are wanting to come and use us, testing everything from memory systems to new bits of electronics to graphics cards to server systems to all sorts of things, including aircraft system bits.
Have you had any encouraging results thus far? Has your group found any faults that perhaps a company had passed over in their earlier design and research stages?
I think probably not passed over, but we certainly have found faults. So when people put the devices in, then they start to see faults almost immediately because, of course, the number of neutrons is significantly more than the environment. I think the surprise is often the rate. So they're either pleasantly surprised that the device is a bit less susceptible than they thought, or unhappily surprised that sometimes it's a lot more susceptible than they thought. There is a problem that actually even similar chips from the same manufacturer with very slight changes can have very different fault tolerance. So there is a problem in the sense that people are looking at about the fact that even what you think is the same electronic device may have very different fault tolerances.
Just one last question. How long do you think it's going to be before this kind of testing is regularly done by electronics companies, when almost everything we use is going to have been optimised to reduce this kind of interference?
I think it's being used quite a lot now. The key thing for us is actually more regulation about it, in the sense that requirements to test on facilities like ours for certain things. The problem with that is, of course, that you need the facilities to do that. So what the UK is doing is providing one of these facilities, both for the UK and for the European sphere, and indeed the world, which will enable people to actually set these down as requirements for testing rather than simply something they would like to do.
That was Chris Frost and me, Priya Crosby, at the British Science Festival 2013 in Newcastle.